Scale of order and lattices is not clickable.
Not?
Clickable.
Oh, is it? But how people read that actually?
Orders and lattices is not clickable.
Let's have a look at the website. What's happening?
Yeah, I'm joining.
Where is Prashanjit? I can give the mic to him to move around. Because it was real hectic to go.
Tutorial, you said.
Yeah, this last one, I guess. Oh, there is another now? Oh no, just 3.
I haven't got the link. Then
এটা আমার কেন লাগবে? এটা লাগবে না। Thank you. You have already joined or not?
Yes, I've joined.
Oh, you can listen to me. Okay.
Yeah, just give me 2 minutes. I'm just coming back. It starts at 10, isn't it? Yeah, 3 minutes.
Yeah. At 10.
is the volume okay or should we?
I guess it's okay. About Sujata's voice you're talking about. YouTube actually.
Can you hear me?
Yeah, we can. So do you want to try to share the slide? Yeah. Okay. So good morning, everyone, and welcome to the second day of our school. So today, Professor Sujata Ghosh is going to continue with her lecture on orders and lattice. So today she is going to consider the ideas about lattices and Boolean algebra. Hope you will enjoy her lecture and can follow it. Okay, it's over to you, Sujata. Please continue.
Okay, thank you. So, welcome to the second day of ISLA, where I am going to give the second talk now. If it's okay, I will close my video and please check if you can hear my voice and everything.
Mhm.
Can you hear my voice properly?
Yeah, we can.
Yeah, okay, thank you. And yeah, once again, if there is any question, please don't hesitate to ask like yesterday, and I would be happy to explain. So let's start. So what were the topics that we covered yesterday? We covered pre-order, partial order, posets, structures and morphisms, then duality, top and bottom elements, maximal and minimal elements, atoms and coatoms, sums and products, downsets and upsets. All these things we discussed yesterday, and we did some tutorial exercises as well in last evening. So yesterday was all about posets or orders, and today it will be all about lattices and its extensions. So without further ado, let's start with the first concept that we need to know regarding posets, with respect to posets, while we approach the notion of lattices. So let's start with the upper and lower bounds of subsets of posets. So take A to be any poset, and then take any subset B of A, then an element A is said to be an upper bound if B is less equal to A for all B in capital B. So the usual definition. And similarly, we can talk about the lower bound. If an element A is a lower bound of a set B, if A is less equal to B for all B belonging to that set. So now, so we can, for any B, we can form the set of all upper bounds of B and set of all lower bounds of B. So you can see my cursor, isn't it?
No, please move it and then I can see that.
Can you see it?
Yeah.
Okay. Yeah. So BU denote the set of all upper bounds of B, which is defined in this way, like for all B in B, set of all A says that for all B in B, B is less equal to A. And similarly, we define the set of lower bounds, the set of all A's says that for all B, A is less equal to B. So in this way, we can define the set of all upper bounds and lower bounds. Now, consider this poset. Of course, here the upper bound of A and C is D, and the lower bound of B and D is A. So that's how we have defined here. Now, if we consider this poset, where we have just changed it, the diagonal arrow. So then the upper bound on A and C becomes B, and the lower bound of B and D becomes C. I hope it is clear to everybody. Now, if this set of upper bounds of B has a least element X, then X is called the least upper bound of B. Very natural definition. And if the set of these lower bounds of B, if they have a greatest element X, then X is called the greatest lower bound of B. Now, here are some interesting cases. Before I move forward, I hope everything is clear to all of you. Okay, yeah. So now there are some interesting cases we can think of. What are they? Everything kind of like regarding empty sets and top and bottom elements. So now if you think of, suppose A has a top element, and then of course the upper bound of A contains the set top only. So LUB A of is top. Now otherwise, if A doesn't have a top element, then of course the upper bound of U is empty set, and so LUB does not exist. Similarly, dually, if A has a bottom element, then lower bound of A is that bottom only. So the greatest lower bound of A is bottom. Otherwise, the lower bound set of A is empty and the greatest lower bound does not exist. Now consider the empty subset of A. Vacuously, we have that all the upper bounds of the empty set is the whole set itself, which means LU least upper bound of that empty set will exist if and only if A has the bottom element, and that bottom will be the least element. Dually, if you can think of the lower bounds of the empty set, that is also vacuously nothing but A, then greatest lower bound would exist if and only if A has top, and greatest lower bound of empty set will be top itself. Any question here? Okay. Now let's continue with some notations. Take any two element set in A. Then the LUB of B, if it exists, will be denoted by X join Y, and this is the notation. And GLB of B, if it exists, will be denoted by X meet Y, and this is the notation. And in fact, if take any arbitrary subset of A, then we will denote the least upper bound of B, which is an arbitrary subset of A, by this notation, and greatest lower bound of B by this notation. Of course, if they exist. For example, consider this poset. Now, if you think of it, B and C, what are the upper bounds of B and C? As you can check, that they are H, I, and top. Do you agree with me? That the upper bound set of B and C are H, I, and top?
Yes, ma'am.
So now, does there a least upper bound of the set HIT? It's not there, isn't it? So B or C does not exist. Am I making sense? Okay. Now, if you consider AB, what are the upper bounds? They are FHIT, FHI top, and FHI top does have a least upper bound, which is F itself, and so we can say that A or B, or A join B exist. Clear? Yeah. Okay, I won't ask you clear or does it make sense again and again. Please don't hesitate to ask me questions. If you do not ask me questions, I will assume that it's clear to you. Please, once again, as yesterday, please do ask me questions. So as you can see, in one case, it doesn't exist, whereas in the other case, it does exist. Now, let us come to the definition of lattice. Take any poset A. If X meet Y, X and X join Y exist for all X comma Y in A, then A is said to be a lattice. For all those two elements, for any two X and Y, if X join Y and X meet Y exists, it's called a lattice. And it's called a complete lattice if the join and meet exist for all arbitrary subsets of B. Then it's called a complete lattice. So if it for any 2xy, if they exist, it's called a lattice. And if for any arbitrary subset they exist, it's called a complete lattice. Now, for example, you can check that the power set of X with the subset inclusion, or the order set, like the downsets of A with the subset inclusion, they all form complete lattices. Whereas if you think of N, Z, Q, R with the usual order, they do form lattices, but they are not complete. Because if you can think of, none of them has, if you consider sets themselves, they do not have a GLB or an LUB. Of course, N does have a lower bound, slower bound, but no upper bounds. So these are lattices, but not complete. So now we would like to give you, so now we have given you started off with posets yesterday, and we have given you a definition of lattice in terms of those posets. But now what we would try to do is, we would try to give you a definition in another way. So to move towards that definition, first let us note that the following are equivalent. By the definition we have just made of a lattice, if A is less equal to B, then A or B or A join B is B, and A meet B is A, and these are all equivalent conditions. Are you with me?
Yes.
Do you agree this intuitively? Of course, you have to write it down. By the way, there are no exercise sessions for this lecture, but I have given you enough kind of results all through the slides. And if you want to really understand this whole topic, please work on them. So this is one exercise. Like, please try to prove that the following are equivalent. So now with this result at hand, let us consider some more identities in lattice. By the way, please prove all these identities. Most of them follow kind of from definition itself. So for example, let us go from like bottom to top. If you consider this absorption law, what does it say? A join A meet B is nothing but A, and A join dually A meet A join B is nothing but A. So it can be easily derived from the kind of the result we just saw. The proposition was we just saw, because A meet B is of course less equal to A. So which means that A join A meet B has to be A. So these are, so that is how we get the absorption. Idempotency is quite obvious. And similarly for commutativity, like the least upper bound of A comma B is the same as least upper bound of B comma A. So there is no difference. So that gives us commutativity. And for associativity, you just need to think about the least upper bound of, like, if you consider the set of upper bounds, the set of upper bounds of A and B or C is the same as set of upper bounds of A and B and C. If you consider the set A and B or C, and if you consider another set A, B, C, the set of upper bounds of both these sets are the same. That's the only intuition you need to have to prove the associativity. So in this way, once again, this is an exercise for you. Please prove these identities in lattice with the definition we just had. So now we are ready to give another definition of lattice. So how do we define lattice? This is a more, we say that kind of an algebraic definition, or it's an algebra in terms of this kind of a definition. So what is this definition? Take any non-empty set A take two binary operations, join and meet on A, and such that they satisfy the following conditions: the associativity condition, the commutativity condition, the idempotency condition, and the absorption condition. If they all these conditions are followed, then we have that A join meet, this structure forms a lattice. Okay, that is another definition. Of course, we should have this, both these definitions should be kind of identical. So in some sense, we should get a partial order from this lattice definition as well. So now here are some results which are kind of expected. Like if you consider any B in A, then the join of A and B is equal to B if and only if the meet of A and B is equal to A. Okay. Now, the other definition is, the other result is define A less equal to B if and only if A or B is equal to, or A join B is equal to B. You can show that A less equal to or forms a poset. And finally, if you consider the least upper bound of AB, it is nothing but A join B. And if you consider the greatest lower bound of AB, it is nothing but A meet B. Since I have given you so many kind of exercises to do, so why don't you let me wait for just 2 minutes, and why don't you try this out by yourself? We have some time, so we have enough time. Why don't you try for yourself? So I am to give you, like, let's say take 2-3 minutes and try to solve for yourself. Are they at least one or two? Are they doable immediately?
Yes, ma'am. Ma'am, just a doubt. So here A join meet is a lattice as defined as the algebraic structure following those properties, right? That's the
Yes, exactly.
Okay.
Shall I continue? Okay, I hope you have got a hand of these things. Like assume that it's a lattice and then try to prove these things. So at least some of, have you got the first one? Second one? Okay, great. So let's continue. So now, as earlier, that both the definitions are kind of equivalent and we are talking about the same thing. That I hope that has been ingrained in you. Let's talk about this substructure, which is again an usual definition that take any lattice. Now take B to be a non-empty subset of A. Then B is a sublattice if for all AB, A join B should be in cap B as well as A meet B should be in B. So that's the whole idea of the substructure as usual. And for example, in fact, as you can see, this is my favorite example of lattice. So if you consider this lattice, let us consider this lattice and let's see which forms, what subsets do form a sublattice and what kind of a subset do not form a sublattice. Now consider these with the unshaded non-green nodes, elements. Do they form a sublattice? What is the condition? I've given you the condition here. For all AB, these are the only 4 elements that you need to consider.
Yes, ma'am, they form a sublattice.
Exactly, they do form a sublattice. Now, if you consider this one, what about them? You just need to consider the unshaded elements here. Do they form the sublattice of the structure?
No, ma'am, they
Of
don't.
course, no, because there are least upward bounds and greatest lower bounds which are not in that set itself. So here is an example which does form the sublattice in the left, and on the right here is an example which doesn't form a sublattice. Now, the next notion is, as usual, the notion of morphism. So let us consider F to be a map from A to B, where A and B are 2 lattices. Now, F is said to be a lattice homomorphism if this condition is satisfied. If A join B is equal to FA join FB, and F of A meet B should be equal to FA meet FB. So this is the condition of lattice homomorphism. Once again, homomorphisms or morphisms, they are nothing but structure preserving maps. And we have heard a lot about structure preserving maps and a lot of these kind of morphisms in yesterday's lectures on both topology and as well as in the category theory lectures. We have, especially in the category theory lectures, we have heard a lot about it. So now, once again, as usual, F is an embedding, if it's an F is an injective lattice homomorphism, and F is an isomorphism if F is a bijective lattice homomorphism. So these are all as usual. And this is we are back to our happy face and angry face example. And we already saw that this was an order preserving isomorphism. Now we say that this was an ordered isomorphism. Now we can also see that this is a lattice isomorphism as well. Are you with me? Okay. So now comes the famous example that we discussed last time in terms of order preserving maps. The first one was not an order preserving map, whereas all the other ones were order preserving maps. Now, can you tell me whether they are lattice homomorphisms as well? Of course, the first one is not even an order preserving maps.
Okay, hold on. Take the mic.
For isomorphism, they have to have order embedding.
Yes.
For isomorphism, they have to be order embedded. So, like if we discussed that they are not order embedded. So,
No, I'm talking about lattice homomorphism. I'm not talking about lattice isomorphism.
Oh.
Okay. Is my question clear?
Yeah, now it is.
So let's quickly consider phi 4.
Phi 2 is not lattice homomorphism.
Why?
Because B and C join will give me D, but
Yeah. So
okay,
then
yeah, because
yeah,
no,
phi
it is.
2 or phi 3 is phi. It is a lattice homomorphism.
It is.
Yeah, phi 2 is a lattice homomorphism. What about phi 3?
It is not.
It is not. Why?
Because join of B and C will give you D, but here B and C of join will give you B, phi of B.
Phi B and C join, phi of B and phi of C join. What are you getting? Isn't it phi of D?
Phi
On the
4
right
or
hand
phi
side.
5?
Where is phi 3 of B? And where is phi 3
Okay,
of C?
I was talking about phi 4.
Sorry, phi 4. Yeah, that I agree. So that is not a lattice homomorphism.
Yeah.
Phi 3 is actually, you can check that it is a lattice homomorphism. What about phi 5? Once again, consider B and C.
It is.
Does it preserve meet always? Is phi of B meet C is equal to phi B meet phi C?
No.
No. So it is not, isn't it? So phi 5 is also not a lattice homomorphism. So you can see that order preserving doesn't make it, meaning order homomorphism doesn't make it a lattice homomorphism. Okay. So you can clearly see that order preserving maps may not preserve meet and join structures. Okay, so there is some to it. Now But we have a nice result. What is that? Is this, are all these clear to you, or you have any question? Then I will move forward.
I think all okay.
Yeah. So if is a lattice isomorphism, if and only if, even though they are not the same in terms of homomorphism, if is they're the same in terms when you talk about isomorphism. If is a lattice isomorphism, if and only if is an ordered isomorphism. You can check it out. Okay. So that is the interesting part. Even though they are not the same, if you consider isomorphism, which is kind of like our intuition would also tell us, if it's an isomorphism, then they are the same. Okay, let's move forward. So now we have discussed lattice. We have given two definitions of lattices, and what we have done is we have considered the usual substructure idea as well as the morphism idea. So let us now consider some interesting subsets of lattices. So the first interesting subset, which is more like interesting to people from algebra, because this concept is being used in algebra a lot. So that is this notion of ideals. So what is an ideal? Let A be a lattice. A non-empty subset B of A is an ideal if the following holds. Basically, what does it mean? It is closed under join, and if any element is there, then and all the elements which are less than that should also be there. So that is the whole point of ideals. So some like straightforward concepts regarding ideal. An ideal will be proper if it is not equal to A. Of course, every lattice is itself an ideal of itself. And the downset of A, you can think of the downset of A, meaning down A, it is actually does form an ideal. And we call that the principal ideal generated by A. Are you with me here? Do you think, what is the downset? The set of all elements which are less than or equal to A. So that is the downset. So you can check that all these conditions would be satisfied there. Because is this clear that the downset forms an ideal? Please. Great. Okay. Once again, example. If you consider this lattice, consider this subset. Does it form an ideal? The unshaded one.
Yes, ma'am.
Join has to be there and everything less that has to be there. It does form an ideal, and it should be clear that this doesn't form an ideal. You're just adding this part and the ideal condition fails. Are you all with me? Okay, fine. Now, so here are some other examples of ideals. Take the power set lattice with union and intersection. They correspond to our join and meet. Now take any finite collection of finite subsets. Then also I forms an ideal. Why? Because union of two finite subsets is finite, and any subset of a finite subset is also finite. And similarly, if you think of take any point x And if you think of the collection of all subsets of X, which doesn't have that point, that collection also forms an ideal. Once again, why? Because if X is not in A and X is not in B, then of course X is not in A union B. And if X is not in A, then of course X is not in any subset of A. So these are other examples of ideals of in the power set lattice Px. So I hope the idea of ideals are clear to you. Now we go into the dual concept filters. We may not have done the dual concept of filter, but I'm like, why am I doing this now? Because it's just kind of a dual concept of ideals. So as I said, the ideals play an important role in algebra, whereas these filters play an important role in logic and topology. And what we will be covered, like today and beyond today, filters will play an important role. So filter is nothing but the dual concept. So a non-empty set is said to be a filter, subset is said to be a filter if it is closed under meet, and if it is closed under the increasing order, which basically means that if B is in there and if A is greater or equal to B, then A should also be there. So that's the idea of the filter. Once again, similarly, we can think of some examples. And before going into those examples, once again, the same kind of idea that it's called a proper filter if it is not A, and the upset, given any A, the upset forms a filter, which we call a principal filter. So I hope the idea is clear. It's the same thing, just the dual idea. So similarly, now you can see that this part, the unshaded portion, will form a filter of the original lattice, which is given there in the top, whereas on the right hand side is an example which would not form a filter. On the left hand side, here is an example which will form a filter, and on the right hand side, here is an example which will not form a filter. All agreed?
Yeah.
Yeah. So here are some other examples of filters. Now, again, once again, consider the power set lattice. Now, take the collection of, as I said, there we took the collection of finite sets. Here we are taking the collection of cofinite sets. What are cofinite sets? It's those subsets of X whose complement is finite. Are we clear regarding cofiniteness? Those subsets whose complement is finite. Now, if you check yourself, I'm not going to do that. You can easily check that it forms a filter. It is closed under meet and it's closed under superset. Are you with me?
Yeah.
Just you need to use the fact that X minus A intersection B complement is A complement union B complement. That's all. And of course, superset. Okay. Now here is an example of from topology. I think Purvita did this kind of structures yesterday. So if you consider, let us consider X and a topology tau over X, and consider any X is in X, small x element in capital X. So now if you consider this collection of this n's subsets of X such that we can say in some sense N is this neighborhood system of X, where all such subsets which contains an open set containing X. All such subsets which contains in an open set containing X. So it is closed under intersection. And of course, it is closed under superset as well. So as you can see that this structure, this collection of subsets forms a filter. Is it clear, everybody?
Yeah.
Okay. Okay, this kinds of ends my discussion on ideals and filters. What I would like to say is, as I said, these filters will occur a lot more in the subsequent lectures. There is one concept that will occur there. I'm not going into the details of the concept, and I would just like to mention it, that is the concept of ultrafilter. What are ultrafilters? They are nothing but maximal filters, which means that they are proper filters. That's the whole point of me getting introducing what do we mean by proper filters. So they will be proper filters such that they do not have any other filter containing them. So in that sense, they are maximal. So they are proper filters, and which means they are not equal to A, and they don't have any other filter containing them. So in some sense, it's a maximal filter. So such kind of a filter is all called a maximal filter or an ultra filter. And it can be shown that any filter can be extended, like it can be shown that when you consider this power set X or some such structures, any filter can be extended to an ultra filter. I think you will get more details into it in the other lectures. I just wanted to introduce the term here. So if you don't worry if you do not understand completely the notion of ultrafilter. I'm sure you will be getting more discussion about it in other subsequent lectures. Just note that it is nothing but a maximal filter. Okay, so now we are ready to have a discussion on complete lattices. Till now, we had been discussing on lattices and some interesting structures or interesting sublattices or interesting subsets of lattices. So let us now focus on complete lattices. Just to remind you, we have that. What is a complete lattice? If the join and meet exists for every subset of A, then we say that A is a complete lattice. So every finite lattice, you can say that it is complete, and any power set lattice is also complete. You can check. And it's pretty easy to see that these are all complete. These are all examples of complete lattices. Now here's a very interesting theorem on complete lattices, and that will give us a lot of examples of complete lattices. So what is this theorem? Consider any non-empty four-set. Then the following are equivalent. By the way, I am very fond of this TFAE. So that's how I denote to say that the following are equivalent. So anyway, so A is a complete lattice. Please note that we do not need to consider join. We can only consider meet. That's what this statement tells us. Meet B exists for all subsets, and the other equivalent condition is that A has a top element and meet B exists for all non-empty subsets of A. Now, how do we prove this? Of course, 1 to 2 is, if A is a complete lattice, then of course meet B exists for all B subset of A. So it is kind of trivial. And what about 2 to 3? How could you say that 2 implies 3?
We have the empty join, which is the top element.
Yeah. So 2 says that meet of empty set also exists, which basically means that A has a top element, isn't it?
Hello?
Yeah.
So why do you say that in the third one, non-empty B?
Yeah,
You
because
could consider all.
that is in the second.
That is in the second one.
I mean, yeah, I just wanted you to emphasize on the fact that the top element is the meat of empty set. That's all.
Yeah, that's exactly what I already mentioned that earlier.
I was busy getting the mic. Sorry about that.
I already mentioned that earlier. Okay, Amit.
Yeah.
Okay. Yeah, it's fine.
So, are you all with me?
Yes. Yes.
So now, what about the like from 3 to 1? So the whole point is you have to somehow define the join. So can you think of defining join in terms of meet?
Yeah, give the mic to him.
Ma'am, so we will take the down set of B and then its complement and the and the and the me and the meat of its complement is exactly the join of B.
Yeah. So here is another suggestion. Why don't you take, so I have to think about it. Like, let me think a bit more about it, but let me suggest a more pretty straightforward thing. You don't really need to consider downsets and anything of that sort. You just consider the upper bound. If you think of the upper bound set, and if you take any B, if you think of the upper bound, and if you think of the meat of the upper bounds, which is nothing but the join of that set. Am I making sense?
Yes, ma'am.
Just think of the upper bounds and take the meat. You will get the join of the set. So that is the whole idea of getting 1 from 3. So please work it out. And I would very much like to see whether the downset idea as well. Please work it out. And yeah, I would be happy if you can send me your proofs by email. Please do work it out.
Yes, ma'am.
Oh, there is a question. Just a
Yes,
moment.
definitely. That's the whole point of dual condition. This holds for all lattices, complete
Okay.
lattices. And we will use the dual meet condition as well.
Oh, she is reading. Okay.
Okay. Purvita, sorry, I can read today.
Okay, no problem.
Yesterday I was not able to read, so I made
Yeah,
some
that's good
changes,
to know.
so I can read today. Yeah, yesterday I was using a different way to present, and today I'm using a different way to present so that I can see the chat.
Okay. Sorry for interrupting.
No, it's okay. Fine. Thank you. Yeah. Is it clear, Visham?
Yes, ma'am.
Yeah. Thank you. Okay. Now, here is a nice corollary of this theorem. Now, consider X be a set, consider X to be a set and C be a collection of subsets of X, which forms a poset under set inclusion, such that arbitrary intersections belong to that collection whenever arbitrary intersection of members of that collection belong to that collection itself. And the second condition we have is that X is in C. So then what can we say from the previous theorem? Can anybody tell me?
C will be a complete lattice.
Exactly. C forms a complete lattice. So that's what the earlier theorem gives me. that C forms a complete lattice. Okay, and moreover, you already have the intersection is in C, which means that the meet will be given by the intersection. And how do we get the join? It's the same idea as I just said. Consider the upper bound and consider the least upper bound. The join will be nothing but take the intersection of all the members of C, which contains the union. Okay. It should contain all those CIs. Na? So you take the union of CI, you consider all those subsets D which contains this union of CI and take their intersection. Is the join idea clear?
Yes, from offline participants.
Yes.
Okay, good. So we are now all set. So this gives us so many examples of complete lattices. Think of, so as you can see, all the things which are closed under intersection and whichever contains that whole set, all such collection of subsets will give us a complete lattice, which means that subgroups of a group, normal subgroups of a group, subrings of a ring, ideals of a ring, ideals of a lattice with bottom, filters of lattice with top, they will all give us complete lattices by the condition that we just saw. Okay, these are, please work it out by yourself, that all these, please convince yourself that all these are actually examples of complete lattices. Okay. What I will now do is go back to your topology class and try to see what kind of concepts that you have that you learned in your topology class, well, which kind of concepts do form complete lattices. So natural things to consider, because we are considering collection of sets, subsets, the natural thing to consider are closed sets and open sets. So let us consider closed sets in a topological space. Okay.
Your voice becomes slow for some reason.
Yeah, can you hear me now properly?
Yeah, it's good. It's
yeah,
good.
I just moved back from my computer. That's why, probably. So closed set, now consider closed sets in a topological space. So of course, closed sets are closed under arbitrary intersection and include the whole set. So the previous corollary theorem and its corollary shows that the collection forms a complete lattice. Are you all with me? See the power of that theorem. You are getting so many complete lattices for free just using that result. Now, the question is, what will be the join and what will be the meet in this complete lattice? What will be the join and what will be the meet?
Ma'am, so join will be the closure of the arbitrary union of the closed sets.
Exactly.
And meet will be the intersection.
Thank you. So join will be the closure of the union and meet will be just the intersection. Is it clear to everybody?
Yes, from the offline participants.
Yeah. Yes, from online participants. Okay. Now, of course, the dual. What about open sets? What about open sets in a topological space? Our intuition tells us that should also form a complete lattice, and it does. So we have that open sets are closed under arbitrary union and include the empty set. So I think, who asked this question? Bisham asked this question. So of course you have you can have the equivalent condition with meet, and that will give you the dual condition of that theorem. The dual theorem will give you that open sets also form a complete lattice. Are you all with me?
Yeah.
Online, offline participants?
It's yes from.
Yeah. So both the collection of closed sets as well as the open sets, they form complete lattices. And this is your join is of course the arbitrary union now, and meet. Can you explain to me why meet is the interior? You just think of the dual condition. So if you consider, let me go back to this condition.
Yeah, your voice is low, Sujata.
Let's me go, yeah.
That's good.
Let me go back to the original, this definition. You just think of the dual thing here. So it should be the union of all the collection which is contained in the intersection. So which basically means that union of all open sets. Sorry, there is something happening. So union of all the open sets contained in the intersection, which is nothing but the interior. Good. So what we have done on complete lattices is we have done an
Again, your voice becomes low.
We have an, yeah, sorry, Purvita. We
Yeah,
have an interesting theorem which has another interesting corollary in terms of collection of sets, which gives us so many complete lattices in so many different areas, theories of mathematics. So now we are ready to get into some other kinds of lattices. In the remaining half an hour, what I will do is we'll get into some other kind of lattices. And the first one that I would like to do is give you some idea of what do we mean by distributive and modular lattices. So take any lattice. Now, it is said to be a distributive lattice if it satisfies the distributive laws. So please note that it would be enough to consider one of the laws. The other one is the dual to the former one. So what is it called distributive? Because of this nice laws that it satisfies, where join distributes over meet and meet distributes over join. So if this condition is satisfied in a lattice, then it is called a distributive lattice. And what about modular lattice? It is a modular lattice if it satisfies the modular law. And what is that law? That law says that or take any ABC in A, if C is less equal to A, then A meet B or C should be A meet B or C. Basically, you can change this bracket interchangeably. So now Can you say anything about the connection of distributive and modular lattices?
All distributive lattices are modular.
Exactly. All distributive, any distributive lattice is modular. Which you can easily check. If you A meet B or C is what? A meet B or A meet C by this. Now, since C is, so A meet B is already there, or A meet C, but C is less equal to A. So A meet C is C. Hence, if a lattice is distributive, it will be automatically modular as well. Here are some examples. If you think of power set lattice, it is distributive. You can think of any chain that is also distributive. Now, for subgroups and group, here is a very interesting condition for the subgroups to form a distributive lattice. One side is kind of trivial, but the other one side of it is really non-trivial. So you can have a look at any suggested literature. Subgroups form a distributive lattice if and only if the group is cyclic. And what about normal subgroups? What we can say about normal subgroups? In normal subgroups, they will always form a modular lattice where what is my intersection and what is my union? What is my join and what is my meet here? In case of normal subgroups, you can think of meet is of course the intersection. Like if H and K are two normal subgroups, that you will then H meet K will be H intersection K, and H join K would be nothing but HK. For those who are aware of group theory, you can understand this notion of HK, why it is so important in terms of normal subgroups. But let me not go into that there. So here are some examples of distributive and modular lattices. Now, here is a lattice which is modular but not distributive. Let us spend some time on this. We just said that normal subgroups will always form a modular lattice. Now, can you think of a normal collection of normal subgroups which will have the same structure? If you can come up with a normal subgroups which will have the same collection of normal subgroups which will have the same structure, then you are through by what we just mentioned here. So let me think of Klein's four group for those who know, and think of all its subgroups. It's a commutative group, so every subgroup is normal. So think of all subgroups of Klein's four group and think of the structure. Please work it out.
They all will kind of contain this structure.
It's just this structure, isn't it? If you think of it.
Yeah.
So let's say the identity subgroup, then let's say E, A, B, A, B. These are the three elements, three non-identity elements. So if you have like A, B, these are the three non-identity elements. So if you have E at the bottom, the set containing E, then the set containing EA, the set containing EB, and the set containing EAB will be at the middle. And the whole set will be at the top. Whole group will be at the top. Are you all with me?
Yes, ma'am. Yes.
So
Yes.
this is the structure of all the normal subgroups of Klein's four group, which we have that it is modular. So we can easily say that diamond lattice is modular. Now, can you show that it is not distributive? Think about these middle elements and take think of, let's say, 0, like the bottom element, the least element to be bought, and the top element, like this element to be top, and let's say some P, Q, R here. Now think of P and Q or R. Can you work it out to see whether it's distributive or not? Meaning I've already said not distributive, so you will see that the distributive law would not be satisfied. Can you just check it out? Meaning sometimes you should check it out now, because it's kind of very easy to see. So think of P, let's say this is P, this is, you can see my cursor, isn't it?
Yeah.
So let's say this is P, this is Q, this is R. And now consider P and Q or R. Will it be equal to P and Q or P and R?
No.
No. So distributive condition fails. So thus we have seen that it is a modular lattice, but not distributive. So now let's consider another example. Consider the pentagon lattice. Okay. Can you show that it is not modular? Once again, consider the middle elements. So if you consider this to be P, this to be Q, and this to be R, we have that Q greater equal to P. Now, can you check whether the modularity condition is satisfied? Anything from anybody?
No, ma'am, it doesn't satisfy the condition.
Doesn't satisfy the condition. So it is not modular. So you have yourself checked that the diamond lattice is not distributive and pentagon lattice is not modular. So, but by the condition we just said that diamond lattices are in fact modular. We just saw. So here we have some examples of distributive lattices, some examples of modular lattices, some example of modular but not distributive, and some example of not even modular. A lattice which is not even modular. So how do we check, given a lattice, how do we check whether it's distributive, modular, not distributive, not modular? Do we do some, like, it's just some ad hoc checking out, which is like really cumbersome, isn't it? Fortunately, we do have a very nice result. And definitely I won't ask you to try the proof of it because it's pretty non-trivial, but it's just working it out, but still it's a bit non-trivial. So here is the nice result that I'm talking about. take it. Sorry, I have, yeah, happily, I should have, I have here said A to be a lattice and here I have replaced A by L. Sorry about the typo. So please consider all these L's to be A. So take any lattice A. A is non-modular if and only if A has a sublattice, which is isomorphic to the pentagon lattice. And A is non-distributive if and only if A has a sublattice, which is isomorphic to the pentagon lattice or the diamond lattice. So this kinds of wraps up the distributive, like at least to how to get to know which lattices are distributive or not and which lattices are modular or not. This kind of wraps up the story. Have you understood this result? Meaning what I'm trying to say here, what at least the what who have proved the theorem tried to say. Okay. So now in the, like, I have 20 minutes now. So I will just, I think I won't go into much details, but let us go into the last kind of lattices that I would like to present in my lecture. That is the Boolean lattices. So before going into Boolean lattices, let me introduce the idea of complements. So let us consider a lattice with the top element and the bottom element. Now, take any A in A. If there is another element B in A such that A join B is top and A meet B is bottom, then B is said to be a complement of A, and we denote B by A prime or A complement. Okay, which means that there is an element such that with which we join with A, it gives us top, and which if we meet with A, it gives us bottom. There is such an element for any A, meaning if there is an element for given an A, if there is an element B which satisfies these equations, then we say that element to be a complement. One important note here, that if you consider a distributive lattice, then any element can at most have one complement. Once again, it's an exercise for you. You can check it quite easily. If, let's say, suppose you consider a distributive lattice and you consider an element A in that distributive lattice, and you suppose it has two complements, let's say B1 and B2. And using the notion of distributivity, you can show that, and the other conditions, you can show that B1 is equal to B2. So any element, if it has a complement, it will have a unique complement in distributive lattices. So, but if every element has a unique complement, then the lattice is said to be complemented. If for the lattice A with top and bottom, if for every element A there exists a complement of that element, then we say that the lattice is complemented. These are just definitions. So let's go into some examples now. First of all, we already know that the diamond lattice is not distributive. So, and you can clearly see from the picture that it has more than one complement. Sorry. Is it clear that if you think of one of these middle elements, it has more than one complement? What is the definition? An element, the complement of an element A is if A meet A is the bottom and A join A, the complement would be B if A meet B is the bottom element and A join B is the top element. So it is easy to see that in the diamond lattice, there are an element having more than one complement. So we see that in the diamond lattice, there are elements with more than one complement. And it is, of course, you see that it is non-distributive and you have elements with more than one. So if you think of the OA, the collection of all downsets, and if you think of the complemented elements, one way to look at it is those sets which are both downsets and upsets. Please think about it more. And of course, in the power set lattice, any element which is a subset, subset of the original set will have a unique complement, which is basically given as take any x, take any A subset of x, then x minus A is the complement in the power set lattice. Okay, so we have no complements, more than one complements, and then we have unique complements as well, examples of lattices. So now we are ready, finally we are ready to define the Boolean lattice. What is that? So it's nothing but a distributive complemented lattice. Of course, when I say complemented lattice, I automatically assume that it has both top and bottom elements. Otherwise, we cannot define complements. So any distributive complemented lattice is said to be a Boolean lattice. Here are some examples. The power set lattice will form a Boolean lattice. This set 0, 1, it will also form a Boolean lattice. And another example from topological space, the collection of Clopin subsets of any topological space, they will also form a Boolean lattice. Please check them out. So now a few properties. This is quite easy to see that the complement of top is bottom and the complement of bottom is top. I think all of you agree with me here. And of course, complement of a complement is the member itself. Do you all agree that complement, it directly follows from the definition? Because A or A prime is top and A meet A prime is bottom, so it directly follows that complement of a complement is the member itself. So now this is what we famously call De Morgan's law, proof that. So complement of A meet B is nothing but complement of A join complement of B, and dually complement of A join B is nothing but complement of A meet complement of B. Once again, you can show this using the, so how would you show this? So you just prove that A meet B meet, A meets join B meet, and prove that that to be zero, that to be bottom. And if you take the join, you prove that that to be top. That's the thing to prove this condition, this De Morgan law condition. Now, finally, you can also check, once again, this is an exercise for you. If A meet B prime is bottom, then A should be less equal to B and vice versa. If A is less equal to B, then A meet B prime should be bottom. Okay, so please check it as well. These are all, like I have given you a lot of exercises throughout. throughout my talk today. If you really want to have a grip on these concepts, please do these exercises.
Shreya, you do have 10 more minutes.
Yeah, I will finish like within 5 minutes.
Oh, that's great.
So finally, we are all set to define Boolean algebra. It's nothing but a Boolean lattice, but as we saw that we had two definitions of lattices. One where we got the our definition from the poset themselves and then continued with it. And the other where we just thought of, considered the non-empty set together with two binary operations. Now, here similarly, we have the concept of Boolean lattice, which we directly get from lattices satisfying certain conditions and certain laws. And independently, we can have a Boolean algebra to be a set with all such these corresponding operations of join, meet, complementation, top and bottom, satisfying certain conditions. So this is how we define it. So take any non-empty set, take the or take the join operation, take the meet operation, take the complement operation given by this, take the bottom element, take the top element. This is the tuple of the algebra we are concerned with. So what are the conditions we need to satisfy? We have that for all A, B, C in A, we have the lattice conditions. Of course, any one of these, one collection of conditions would have sufficed. Just for the sake of it, I have written all along, I've written both the conditions. So we have the associativity of join and meet, we have the commutativity of join and meet, we have the idempotency of join and meet, we have the absorption laws of join and meet. So these are given by the lattice conditions. Then we have the distributivity condition. A meet B or C is A meet B or A meet C, and A meet B join C is A meet B join A meet C, and the other one. And finally, we have the complementation condition, which are given by these two conditions. So A join bot is A, and because we already also have this top and bot, A join bot is A for any A meet top is A for any A, and this is the last one is basically the complementation condition. A join A prime for any A, there is this A prime, A join such that A join A prime is top and A meet A prime is bot. So this is what we have in our Boolean algebra. So I will finish my lectures with some examples. So this power set with union, intersection, power set of any set X, like complementation, empty set, and the whole set, this gives us a Boolean algebra of power sets. Now, if you consider all finite and cofinite subsets of X, okay, and if you consider union, intersection, complementation, an empty set and X, then also the whole set, then also you will get a Boolean algebra. Okay. So are you convinced that if you take union, intersection, complementation, it will all be inside? And of course, empty set and X are also there because empty set is finite and complement of X is empty, which is also finite. So empty set and X are there, and if they are there, they're automatically the bottom and the top elements, and we have closures under union and intersection. So once again, as I already mentioned, the set of Clopin subsets of X endowed with a top, of X, which is endowed with a topology. Otherwise, you cannot define those Clopin subsets, which are both closed and open subsets. Once again, the same union, intersection, complementation, empty set, and X. Please note that all these examples are kind of set examples. And in that sense, all these examples are called set algebras. They're all kind of subalgebras of the power set Boolean algebra of the power sets. So in that sense, these are called set algebras. And I will finish with an example which will be used, I will presume, a lot in the next few classes, is the simplest Boolean algebra, which is the set 0, 1, and OR is given by the join operation is given by basically the maximum, meet operation is given by the minimum, complementation is complement of 0 is 1 and complement of 1 is 0, and 0 is the bottom element and 1 is the top element. So with this, all these examples, I finish my lecture. Thank you.
Thank you so much for such a nice lecture. So we do have 5 more minutes. So if you have any questions regarding the exercises, whatever she has given to you, or you have any doubts regarding whatever she explained, please feel free to ask.
Yeah, I also should mention that Vinod, thanks to Vinod, he has pointed out certain typos in my this sheet. The exercise sheet. I will change them and I will upload them again. It's not major typo. It's just some small typos are there. It doesn't change any question or anything. Yeah. So I will change them and upload them again once again. And of course, if you have any question, please don't hesitate to email me. All these lecture slides will be available. And if you have any difficulty to like with any exercises that I have given you, proving any theorems that I have given you today, please don't hesitate to contact me. Please don't hesitate to contact me at all.
Okay.
I had a question about ideals.
Yes.
So I was thinking that if we think of the lattice as a ring with addition given by join and a multiplication given by meet, then the notion of ideal over here will coincide with the notion of ideal in a ring, I think. The only difference is that it's not an additive, it's not a group under addition.
So can you tell me again?
So I was thinking, whether we can turn the ideal that we defined here into an ideal of an actual ring. And I was thinking that the addition can be given by the join operation and the multiplication can be given by the meet operation. And it forms a semi-ring under these operations, as in the addition doesn't have an inverse. And under these things, it actually becomes an ideal in the sense of a ring.
So what we in a ring, you have the group as well as the plus and dot. So addition, in terms of addition, it forms a commutative group. And in terms
it forms a semi-group, I think. Like it forms a monoid. I'm sorry. Yeah. Because it.
No, with respect to multiplication, it forms a monoid, or whichever way you want to describe rings, isn't it?
Actually, it will be a semi-ring, I think, because like there's no way to invert it.
Yeah.
So in a semi-ring, it will be the ideal. Like if we define
I think so. I have to think about it.
If we define the ideal of a semi-ring in the same way as we define the ideal of a ring, then I think the two notions will coincide.
Might be. So because we were saying ring, I got a bit confused because in general, we have rings. When we say that it's a commutative group and with a dot operation, it's a monoid or a semi-ring, meaning, or a semi group.
Right. Yeah. Here I need to restrict it a bit and make it a semi.
You need to that definition won't follow. You would need to restrict them in some sense.
But if we define the ideal of a semi-ring, I think ideal of a lattice and ideal of a semi-ring will coincide.
In fact, ideal of lattices and ideals of rings, they have a very nice connection. I presume it will be like, in terms of, you could think of categories as well. I presume it might be taken up
Okay.
in the theory lecture as well.
Okay.
They
So,
form an, yeah, they form
Also,
an,
we usually don't define filters of a ring. Like that's what I.
meaning in general, as I said, the ideals are more, ideals are more interesting. When you can define filters and ideals in all cases, but ideals are like historically or traditionally, ideals is a concept that are more used by the algebraists, whereas filters, the concepts that are more used by the logician and topologists. There is nothing like more to it, I would say, at least
Right.
from the long knowledge I would.
Oh yeah, and in a ring, like I think the filter will just become the entire ring because it's a group under addition. Like we take a multiplicative.
There is no harm in
Right.
considering any such concepts.
so
Right.
Yeah. Thank you. Yeah.
okay.
Thank you.
So it's already 11:30. So I think that you may continue discussing. There is no problem. But we do have a tea break right now for 15 minutes. And we will come back by, say, 11:42 because we will start that next session from 11:45. Okay. So now you can just discuss with Sujata Di, whoever wants to.
Is there any question? Other question? Current urgent question now?
Thank you. So it's already clear, Anand. Do you have any doubts or you want to?
I don't think Anand had any doubt. He was
He was just
explaining
discussing
what he was thinking about different ideal concepts as well.
Yeah, I just wanted to say that if he want to continue, he may.
Yeah, I would be happy to continue.
Yeah. No, I think it's clear now. Like I was just wondering if there's a connection between like the kind of ideals that we generally talk about in the context of rings and these ideals, and yeah, I think that's clear now.
এই সবুজ বোতলটাও নিয়ে যেতে পারিস, সবুজ বোতলটাতেও আছে, আম পান্নাটাও নিতে পারিস। ওটা কি চা আছে নাকি? ওটাও নিয়ে নে, যেটা যে খাবে ইচ্ছা। ठंडा ही है, छोटा ही वही है। उसमें थोड़ा सा और पानी डालने से ठीक है, और ठंडा हो जाएगा शायद, ठंडा पानी डाल दे। ओह ना, सॉरी।
आपको natural transformation चाहिए.
Okay. Okay, now we are starting our second session for this day. So, for the online participant, are you here? Hello?
Yes.
Has 15 minutes. Okay, so for this sessions, first 15 minutes will the lecture is delivered by Animesh, and then rest of is done by
Dipankar will start from 11, and then after Dipankar's, I will come back. This first 15 minutes.
Okay, okay. So he will start where he finished yesterday. So let's.
Yeah. Okay. So so yesterday we ended our natural transformations, and I gave you a very a concept which is within us from our childhood days. Determinant turns out to be a natural transformation. But before writing the definition, let me clear out, let me make some rectifications from past lecture. So initially, when I was defining this functor from this to okay, a functor from sets to real vector spaces, someone from the online audience gave me a assignment. That is, I take a set S and I map it to a collection, set of all set maps from S to R. This is a real vector space by pointwise addition and scalar multiplication. But that person only gave me the object assignment. To define a functor, I need assignment of arrows also. So, and what I will define the assignment on arrows is something very trivial or something very obvious. So if you begin with a map from T to R, that is an element here. So it will look like something like this. You want a map from S to R. So something S to R. You have a map S to T, F. So you just you compose F with it. So you get a map from here to here, which takes an arrow, say G, set map from T to R, G, and maps it to G composed F. So basically blank composed F. So this, note that this is reversing the direction of the arrow. We don't want that in a functor, because functor, as we defined, takes an arrow to an arrow. And but this is not an arrow. This is not taking an arrow to an arrow. It's taking to its formal inversion. So instead of defining it in this way, what we do is a sort of a trick. We put first of all an opposite here. What this effect will do, it will do the following. We begin with an arrow in sets. This is in sets. In sets op, it will look like say S to T to S in sets of, and then we map arrow to an arrow without any shifting, without any inversion. We do it first here, and then the definition of this functor is valid. So that's a contravariance, which reverses the direction of an arrow. Most of the time when we write the corresponding arrow below, we don't write it in sets op, we write it in sets, and then the inversion of the arrow is shown here. So that's one of the questions that was raised. The member from the online audience gave me just an object assignment, and this is the natural arrow assignment that you can give it to turn it into a functor. So that's one clarification. The next clarification is as follows. Someone from the audience also gave me another assignment, which is you begin with S to T, and you map still home sets from S to R, but you can possibly define a map in the same direction from T to R, and that same direction map is as follows. It will take an arrow G and will map it to the following function from T to R. You define, say, G tilde from T to R by taking an element of T and mapping it to the following. Yeah, where you map to 0 if T is not an image of F. F is there, image of F. And when when T is in the image of F, you do something different. What you do here is the following. So T is an image of F, right? And you take, so T, small t is here. I pull it back. I get a subset of S that is F inverse T, subset of S. And now you make a choice. Take an element S sub T, small s sub T inside of it, and then use this person, G. G is a map from S to R. What you do, you take ST to GST. And that is a valid function. And so what you do here is GST. Now, is this a functor? It's not. Why it's not? Because the choice of small sub st here, you have to make a choice here because this is a subset. And whenever you have a situation dependent assignment, more often than not, that will not be a functor. You can check here that composition won't hold even if you, it's a good exercise, you can check. So that's the clarification. Another remark, if I somehow remove any choice that I can make here, say when F is injective, then F inverse T will be a single element in S, and ST, there is only one choice for ST. So what I will need to do here, I would simply, okay, so this functor will not be contravariant, it will covariant because it's taken an arrow to the same direction. I need to just, if I do injective, then this is indeed a functor. What this category is category of sets with category with objects as sets and arrows between them as injective maps. Not all maps, injective maps. And then this will be a functor. So these are the clarifications that I needed. Okay, so now let's go back. So we were on, we made the following diagram yesterday. We had this group of n cross n linear matrices with entries in ring R, and we had this group of units, and we had GL and S for another ring, and we had its group of units. And we began with a ring commutative unital ring homomorphism And we made this functor, we made this diagram, GLN phi and phi, and this is determinant for ring R. This is determinant for ring S, and we said that this commutes. Now let's go, and we say that this makes determinant a very good example of a natural transformation. So let's give what is a natural transformation. Okay. So definition. Oh, yes, sorry. So definition. Begin with two categories. So let C and D be two categories. Take any two functors from C to D. So take C, D, and so this is a functor F, this is a functor G. Two functors with same domain and codomain categories. In this situation, a natural transformation alpha denoted F2G is the following data. What is the data? You have a collection of what arrows? Alpha is the following collection of arrows, one for each object of category C. This will be alpha sub C from FC to GC, and C is in the objects of C, category C. This is just the data. I need some more conditions on it. The condition on it is the following, such that for any F C to C prime in C, the following commutes. Well, what commutes? This is an arrow C in C. Arrow will be taken by F and G to distinct, possibly distinct arrows. So first action of F on the small f will give me this F C prime. This will be FF. The other way around, I will have G. So GC to GC prime. And this will be GF. And now these data come into play. FC to GC, that will be alpha C. And FC prime to GC prime, that will be alpha C prime. And this commutes. This is my condition. So this is a natural transformation between two functors, and we denote it by this. So to denote that this is a notion of a morphism of functors, just like that. That defines a natural transformation where arrows alpha sub C here are det sub R, one for each R. So this will be denoted by this commutative unital rings from to group. Oh, sorry. Commutative unital from rings to group to this will be the GLN functor, and this will be the units functor, and this will be the determinant natural transformation. One for one arrow for each object here in an arrow will be here. So that's a natural transformation. Sorry. No, you want an arrow of D indexed by every object of C. Yeah. Yes. So it can be empty set. Yeah. Okay. Then it not be natural transformation. Exactly. That's what I'm. So it can be it exists and it called it up. Otherwise. One case may happen is that for an object see here, FC and GC are disconnected. They may not have any map between them. And in that case, there will not exist any natural transformation. Yeah. Okay. In discrete categories that will have. Okay, so that's definition.
It's not really set.
Yeah.
It's not a set. So this is given by this data set. If so, some collection of arrows in the codomain category satisfying this condition, that is a natural transformation. Whether there exists or not is an independent question. Okay.
So everything actually happens in the codomain category itself, right?
Yes.
Yes. The arrows are in the codomain category, category D.
Right. Right. Okay.
Okay. So just one more trivial example, just to get the definition straight. The following is a natural transformation. You begin with you begin with you begin with sets, and you map to sets again, and you make the following functors: ID, the identity functor on sets, and the power set functor, something which we introduced last time. And the natural transformation here, let me denote it by alpha, and the components, these arrows are called components of a natural transformation. For each object C, alpha C, FC to GC, we call them component of natural transformation alpha at C. So the components of this natural transformation for a set X will be given as the following. First, ID of X to P of X. ID of X is just X. And so define this map, because this arrow will be in sets. So I need to define a set map, and I do this X to singleton X. Check yourself that this diagram commutes in that case. Okay, so that's for natural transformation. There are more examples in today's tutorial. We will solve them. And now Dipankar will talk about what is the natural notion of when two categories have the same information.
Okay. So, since yesterday, we have been talking about abstract nonsense, as people call it, named category theory. It might be too heavy for people. Okay, so so that part is erased. There was a list of categories, and where we listed objects and morphisms and so on. Well, I want to fill this up for references, maybe. By the way, online participants are not really responding to my requests. So I request everyone to turn on their video today and want to see how their faces look like when they're listening to this abstract nonsense. Why don't you turn on your videos, all of you? Just turn on your videos. I want to see your faces. Everybody, please. Yeah, I'll talk to them. Now, once you have turned on your videos, so there was this question asked last time. What is your favorite pure mathematical theory? Oh, I remember someone said complexity theory. Who was that? I don't know what complexity theory is, but I don't think it is a pure mathematical theory. It might be applied. So give me some, like, for example, Aditya, can you tell me about your favorite pure mathematical theory?
Group theory.
Yeah, group theory. Okay, so you have this category of groups here. What do you think that the object should be? We talked about this last time.
Morphism.
Sorry?
Homomorphism.
No, what should be the objects in this category?
All groups.
Okay, all groups you mean. And morphisms as group homomorphism. Right. Now, what about Anand? Anand, can you tell me?
Yeah, how about the category of R algebras or something for a fixed ring R?
R algebras. Given a ring R, you can talk about R algebras where objects are all R algebras. And you take R algebra homomorphism, right?
Yeah.
Right. Okay, I'll tell you one which no one is pointing out. Is sets is my favorite category. All sets. Don't forget that. And functions. Okay, some people last time told me about matrix spaces, and there were matrix spaces. Matrix spaces. And then you have either continuous maps, or you can have homeomorphism or matrix preserving map. You have topological spaces, top spaces, and continuous maps, and so on. So in the last two lectures were on pre-orders or posets, whatever you like. You had pre-orders here and monotone maps. And this were the last two lectures. All right. Now to start with, I want to point towards an exercise that was given in last tutorial about orders. So there was this question, are all order isomorphism and bijective order preserving maps same? There was this question, right? Order preserving bijection and order isomorphism. What was the answer? Can someone tell me?
Yes.
And what about the rest? No. Okay, I'll give you an example. Think of this situation. Let's say A, B here, C here. This point. And then this 3. You can see that there is a order preserving map, right? This is a bijection, right? But can you construct a map from here to here, which is an order preserving map? No, right? This is a bijection, order preserving map, but this is not an isomorphism, order isomorphism. So you realize that while talking about a mathematical theory, if you want to understand how two things are really equal or identifiable, then you should be giving importance to the structures that you have and identify them using those structures, not just set theoretic bijection, not just point-wise identification. The structure matters. And in this sense, order isomorphism is not really bijection of sets, which is just an order preserving map. So this tells you that to talk about isomorphism in a mathematical theory or identifying two different objects in a mathematical theory, you should better give me two maps in that category itself, which sort of act as inverses to each other. And what do I mean by that? Okay, so let me make a definition out of it. Nice. Definition out of it. So let C be a category. And F okay, from A to B be a morphism F is said to be an isomorphism if there exists a map from B to A such that when you compose them, they become identity on the corresponding object, meaning that, so let's say you have a map G, so that G compose F is identity on A. On the other hand, F compose G is identity on B. So this is the diagram. Sorry. Right. So that is the notion of an isomorphism. So I want you guys to fill up this table now. So I want to put isos, let's say here. Who's the person who told me group theory? Where is he? I don't remember his name now. It was Aditya, if I remember correctly. What should be the isomorphism in groups?
1 on 2.
Sorry?
1 on 2.
1 on 2. So they are called group isomorphisms. Okay, in this case, note that just homomorphism with bijection does the job, but not in all cases. I'll tell you that in all algebraic examples, bijective maps would do the job. So this is bijective algebra homomorphism or algebra isomorphism. Okay. What about sets? Well, they are bijections, right? What about topological spaces and continuous maps? What are they called? Homeomorphism. Note that a continuous bijective map need not be a homeomorphism. The inverse need not be continuous, and therefore that is not a good notion of identifying topological spaces. What about pre-orders or partial orders? Order isomorphism, right? That's where we started. And matrix spaces, you can still put homeomorphism here. Okay. So that's about isomorphism. Well, now you can tell me, now you can ask me maybe. So you are talking about identifying structures in a theory, inside a theory. What about yourself? You are a category theorist. Shouldn't you be able to identify categories, right? You might have this question in your mind for me now. Well, why not? You just have to mimic what I wrote here. So how do you mimic this? So I mimic this in this way. Instead of putting to object here, let me put to categories and a functor. Let's say A and B for that matter. Be two categories and F a functor. We would call F an isomorphism if you have a functor in the reverse direction, such that G compose F and F compose G both become identity. So you can call it a definition maybe, but I'm not going to explicitly write that. If G compose F is identity functor or ID on A and F compose G is identity on B. By the way, if you look at this definition, you might wonder, oh, there exists one. You can check that there cannot be more than one if it exists. Okay, that's a simple exercise which everyone would have seen in algebra sometime. So that is an isomorphism of a category. Well, that seems to abstract a notion. Let me give you an example. Well, I want to come back to the last example I gave you, the example which allowed Purbita to talk to Sujata, as I would say. So there was this category of pre-orders. And there was this category of topological spaces, right? I gave you one arrow or a functor from topological spaces to pre-orders. Do you remember that? It was the specialization functor. Did you check that? It's a specialization functor. How many checked it? Did any online participant check that this is a functor? Anyone? What about Krishnendu? Did you check it?
No, I didn't check it.
Yeah, okay, fine. Well, that's a practice. I would say that some category theorists themselves do the same. They do not check it. They just say that this is an assignment. It better be a functor. But just check it if you are a newcomer to this. So I told you that how someone from some order theorist can answer a question whether a topological space is T0, T1. But what about the other side? Can a topologist answer some question about pre-orders? I didn't give you any functor from p-orders to topological spaces, which can transfer data from p-orders to topological spaces. I think Purvita would be upset, but there is this upset functor. What does it do? Given a pre-order, what you do is you send it to the poset P itself with a collection of all of its upsets. I'm upset. So write whatever you like here. You can check that that gives you a topology, right? Someone, I remember that someone told you about that, but not exactly. Okay. So now Purvita can answer some questions about pre-orders maybe. But is this an isomorphism of categories? Once I say that they can talk to each other, the communication may not be so good. Is this really an isomorphism as I introduced here? Is this? You check. So what does this functor do? Well, if you take this composition with upset, then you can check that this is actually identity functor, which is identity on pre-orders. But if you go to the other direction, that will fail to be an identity. That won't be equal to identity. Just check that. I don't want to do that now, but it does not work. Okay. So therefore, their communication is not going to be so well. What I'm going to do is I'm going to put some condition here, what is called an Alexander topological space. Those are topological space where arbitrary intersection of open is open. So the definition of a topological space was saying that you have finite intersection and arbitrary union, but Alexander topological spaces are some nice topological space where moreover you have all intersection, not only finite. Now you can check that this still stays a functor. Now you can check that this really becomes an isomorphism. So there is upset. So this really becomes an isomorphism. But do you realize that while making it an isomorphism, I had to forget something, right? I had to forget some data from top. I removed some topological spaces, which are not nice, to get an isomorphism. So we have to lose something if we really want to talk about isomorphisms. It doesn't sound to be so good an idea. And in fact, most often in mathematics, you find out different theories which have some similar properties, but they're still not isomorphic. You cannot find an isomorphism. Let me give you an example of that. So last time, Animesh told you about these two ideas, that on one hand, you have the category mat R, matrices, morphisms are matrices, and on the other hand, finite dimensional vector spaces. I'll put a star here to indicate there with a choice of a basis. As he said, I'm just following him. So this was the category where you had integers as objects, and between two integers n to m, you had a matrix which was of size m by n of real numbers. Okay. And on the other hand, you had vector spaces, finite dimensional, with a choice of a basis, and morphisms were basis preserving linear transformations. Right. He gave you this assignment, if I remember correctly, which was send a vector space to its dimension, right? Which is dimension. But often doing linear algebra, you do not distinguish between these two ideas. A finite dimensional vector space is just as good as considering Rn itself, right? And a linear transformation, just as this matrix, it's matrix of linear transformation, right? You do not distinguish most often. So therefore, these two ideas should somehow be similar to you. But you see how they are similar in the language of categories? Well, so this side, so he gave you this side function, which is dimension. What I'm talking about is sending an integer n to Rn. This is the model where you are going to send n and consider everything. Things sounds to be so good. But once again, if you really try to check whether this is an isomorphism, this is not. Yeah, so I mean, this is the functor. N sent to Rn, yeah. So, right. Now, what happens if you compose? On one side, you do get identity, the dimension, compose R blank. If you look at that and take an integer, you do get back n. What about the other side? If you take R blank and compose with dimension and take a vector space, what do you get? You get Rn back, R to the dimension of V. Well, that is not exactly V. We have some information. So, well, I'm being sloppy here. I'm not writing R with a standard basis. This should be written as standard basis, as I have choice of a basis. You put that. So this is not exactly what we started with. It is not V. It's not V. But this is nonetheless isomorphic to V. Though this is failing to be an isomorphism, you see some nice condition that they're isomorphic on object level, though not equal. So this is an idea which I'm going to introduce. Instead of isomorphism, I'm going to call them as equivalences of categories. So to modify this, I'll write a definition here. An equivalence of category is a data that is to functor f and g on different directions or reverse direction, so that when you compose, they're not exactly equal to identity, but they're isomorphic to identity functor. What do I mean by that? I mean to say that for every object, so okay, let me write that. So which means for all object, let's say A inside A, you have GFA is isomorphic to A, and FGB is isomorphic to B for all B in B. Sorry, my bad. So that is what I'm going to. Now, if you notice carefully, if you are really going to be careful, then you would say, we have written isomorphism of two functor. What do you mean by that? One should correct this and say that, oh, there is a natural transformation whose components, as he wrote, all of its components are isomorphism. But let's not go into that, this just means that there is something natural about this isomorphism. But this is the idea that on object level, they are really isomorphism if you compute. So this is the idea of an equivalence. And now please check that or verify or put ideas in your brain and convince yourself that this is really an equivalence of categories. So this is an equivalence. Let me put it as example one, if you wish. Is it clear? about online participants?
In the previous example, which is posets and topology, can
Yeah.
we add some new structure to the poset category to make them some sort of equivalence?
Well, no, you see,
because in topology category, we removed certain structure, and so in
so the
pre-order,
correct
can we add
sentence
some
would be,
structure?
the correct sentence would be, Sujata can say anything about topologies, but Purvita won't be able to talk about any pre-orders, which is to mean that if you really start from let's say topological spaces, you go to pre-orders with specialization, then you get posets. And if you start from pre-orders and you try to go there, you really land on all topological, you really land on topological spaces, but that does not cover all of topological spaces. There are topological spaces which do not come from pre-orders. So which means that this functor, this upset functor is going to embed it inside. So this upset functor, if I write correctly, then is sending to top, but this is not going to collect all topological spaces. This is going to be some sort of an embedding. It is not going to give you all topological spaces. So there is nothing to put in poset side. It's better that you put in topological spaces some restriction. Is that clear?
Yeah.
Does downset is also a functor?
Something like that will be in the tutorial. So I'm not going to give an answer to this. We'll talk about that in the tutorial. Okay. I hope that is okay.
Could you once go over the conditions of equivalence?
Yeah, sure. So an equivalence of categories is a data where you have two categories A and B, and to functor A from A to B, and on the reverse direction you have a functor G from B to A, such that when you compose these two, FG, let's say if you compose G with F, you start at A, go to B, and then come back by G, you need not land exactly at the starting object, but you land at something which is isomorphic to the object. So this is the condition. And on the other hand, if you start at B, go to A, come back by F, you need not land where you started, but something isomorphic. So equality is in some sense evil to category theorists. So I hope that is clear now.
Yeah.
All right. I don't know how much time I have, but I really want to bore you guys with some vector space example now. So, well, why not vector spaces? They're really good. Most of you know linear algebra. So let me ask you questions from linear algebra itself. Do you know what is a dual vector space? Sorry, Nara. What is a dual vector space? Yeah, you. What is a dual vector space?
Vector space of linear functionals from the space to the field.
Right. So you have a vector space, 0, and so on. What do you want to do? You want to send this vector space. So this is the dual notion. So this dual, you want to send this to the set of linear functionals, right? So this is the set of linear functional denoted V star, which is the set of all vector space map or linear transformations from V to, I'm not going to write the whole of it. You just understand this. You have V to R. This is just the home in this category. And you have usual addition, zero functional, and so on. So it's a dual notion. You realize that you are actually in vector spaces, in the category of vector spaces over real, let's say. And you are landing to itself. Okay, for the moment, let's consider finite dimensional only. I don't want to go into discussion which is complicated. So let's make our life simple. Finite dimensional. So you have given me this dual. Is this a functor? Do you think? Okay, so if you have, let's say, W and so on, how do you map it to W star? Well, W star is but W comma R. So this is to be understood as home, okay? I'm being sloppy here. I want this. How do you construct this? He just gave you an example that you,
Contravariant in some sense.
Yeah, so he gave you this example now. This is really the functor what someone talked about earlier, right? So this is the dual. So this better be reverse, right? So this is the contravariant functor. So what I'm going to do is I'm going to put a dual over here, an opposite sign over here to make it covariant in our sense. So yeah, you can still think of it as a covariant functor. Now, so therefore we have a functor, check. Now that this becomes a functor, why not this direction, the same functor? So this is the dual functor. Why not the same functor in the different direction? You can put opposite on the codomain, it still stays as a functor. So you have this two functor. What about this two? Is this an equivalence of categories? What do you think? Just try to compose them. What are the composites? Well, if this is my F and this is my G, then what is FG? It's just going to be the double dual. So on a vector space V with the structures, this is going to be the double dual of V. And for a finite dimensional vector spaces, do you know this? That they are isomorphic to the starting vector space, right? And also on the other side, if you start with GF and take the same thing, this is going to be W star. This is going to be just W itself. Right? Isomorphic, sorry. Yeah, that's the important point. They're not really equal, but they're isomorphic. So this is an equivalence of categories, of course, with an opposite notation, but that is, so this means that the category of vector spaces is equivalent to the category, to its own dual category. Okay, great. So this is example 1, this is example 2. Right. Now you can ask me, when we studied bijection in set theory, my teacher told me that you can really say some properties about this assignment like injective and surjective. Then you can be sure that this is an isomorphism or a bijection. Then you can ask me, is this true here? Can you extract out some properties so that happens? Yeah, indeed, you can. So so what I want to do is that I want to forget about the inverse side functor in this case, let's say, by extracting some properties. What properties does this functor have? I'll erase everything here. This property has this, this functor has this property. Take a finite dimensional vector space V with a specified choice of a basis. This, I know that this is isomorphic to R to this dimension, right? With the standard basis. Don't I know that, right? And this was exactly this functor, R blank, applied to the dimension of V. So there is an object, this object belong to the starting category, mat R, right? So there is an object in the starting category whose image is isomorphic to a given object in this, for every given object, right? What more, this is the philosophy or a psychology of every student that a matrix of size m by n is as good as a linear transformation, which is to say that the set of all matrices of size m by n is exactly equal to the set of linear transformations, which is, so this is going to be linear transformations, or I'll write home finvect R of Rn to Rn, right? The set of all linear maps. These two are the same thing, or there is a bijection, right? So this functor, so this is, but this is what? This is the set of all morphism in matter from n to m, right? Isn't it? So therefore, this functor is really mapping the home to the home itself, of course, up to a bijection. So it is giving a bijection on home set level and some sort of identification on the object set level, object collection of object level. So this is what is going to give you an equivalence. That's what my claim is. I'm not going to prove it. So this idea that there is an object whose image becomes isomorphic to a given object is called essential surjection. So I'll write a definition, but that is not worth pointing out. So a functor f from C to D is called essentially surjective if for all D in D, there exists a C inside C such that D is isomorphic to f of C. And the idea that a functor on home level is just a bijection or not changing anything is called fully faithful. And f is fully faithful if on home set level the assignment is a bijection, that is in C this is a bijection FA to FB. So this is a bijection. So F being sent to FF is a bijection. So I'd like to point out this theorem, which is giving you a similar criteria for defining an equivalence. So a functor f from C to D is a part of an equivalence, meaning that there is a reverse side functor is a part of an equivalence or an equivalence if it is essentially surjective and fully faithful. Okay, so that defines yeah, of course one side I already proved and another
what do you
side.
mean by part of an equivalence?
So there is this data now. G is also a part of the data, the inverse side functor.
Okay.
So by that, right. All right. Now, good. It sounds good, but I'm still not finished with finite dimensional vector spaces. I still want to bore you with this. This is just to emphasize that you can have covariant functors from finite dimensional vector spaces to finite dimensional vector spaces, which is just the composition. Take double dual, and then you know that every object here is isomorphic to its double dual. Therefore, this also gives you an equivalence. Just show that the fully faithful condition is there. Is there any question from the online participants? No. Great. So I have a view. Okay, fine. Time is not a constant here anymore, I feel. So I want to erase everything. I'm bored with this finite dimensional vector spaces, finite dimensional vector spaces. And maybe advanced people are already bored with all of this. Let me give them an example which they can connect to. If there is an algebraic geometry over here, then I'll give you this example. Take the category of rings, commutative initial rings, and the category of affine schemes within F. This is not for everyone.
Voice is not audible, actually.
My voice is not. Hello. Hello. Can you hear me now?
Not really. I mean, I can understand, but I cannot see.
The battery is dying. All right. Hello, can you hear me now?
Yeah.
Yeah, so there is this complicated example for someone, but easy for algebraic geometers, which is take the category of commutative unital rings and affine scheme on the other hand, and take this functor spec, which takes a ring R and sends it to spec R with Zariski topology. And on the other hand, you take the sectional functor, which is given a scheme x comma ox, you send it to this ring, but that is not for everyone. If algebraic geometers are bored over here, then I'm trying to entertain them. So this is an example. All right, let's not go into complicated things. Still, I feel that this definition is a bit hectic for some of you. Let me give you some pictorial idea. Let's say you have two different set x and y with two different equivalence relations, xr and ys. As far as equivalence relations are concerned, when you identify these two, so x and y are two different sets. They could be very different. Let's say this with 3 elements, this with 50 elements. But they could be different. It is given to you, let's say, with some equivalence relation data. When do you identify this two as far as equivalence relations are concerned? You look at their congruence, x mod r and y mod r. If you can say that they are really equal or at least bijective, then you can say that up to equivalence relation, they are the same thing, right? That is. So what does this tell you in a pictorial view? So you have a set here and you have equivalence classes. You have equivalence classes. This could be a very large set and you have equivalence classes. This should be same if you have a bijection between those equivalence classes. Right? What is happening in an equivalence is that if you have two different categories, let's say instead of sets, think of this as categories, an isomorphism between two objects being an equivalence relation, you can check that this really is an equivalence relation in some sense. Then if you collect all isomorphic objects, they're going to give you some sort of equivalence classes, right? Which is called the skeleton, by the way, with morphism between them as morphism of objects. Then we say that C and D are equivalent if the skeletons are equivalent. That is, you can find an isomorphism of the skeletons. Okay, so that is one sort of pictorial idea. Okay, I think I'm running out of time, but before ending, let me give you one last example, but that is going to be maybe complicated. But what I want to do is I want to connect
Sujata's talk on order theory to a set theorist by an equivalence. What is that? So for the next few minutes, I'm going to write something on the board and you are going to tell me what you have learned here. Complete atomic Boolean algebras. You have heard of each of the terms? What is complete Boolean algebra or complete? What is, first of all, Boolean algebra? It was just maybe half an hour ago, right? You have all joins, all meets. That is complete Boolean algebra. I mean, Boolean algebras are distributive lattices with negations. And complete means you have all meets. What is atomic? There is a set of atoms, right? Which can give every element as a joint. So you have this category of complete atomic Boolean algebras, CABA. You understand this? And morphisms are Boolean algebra homomorphism, which preserve every structure. And on the other hand, I have this category of sets. Okay. Did you see this power set function? Take a set and send it to its power set, then it becomes a complete atomic Boolean algebra where meet is intersection, join is union, and you have negation as complement, and you have atoms as singletons, right? This structure. Of course, you have top and bottom element, which is this complete atomic Boolean algebra. You can make it a functor. I'm not going to tell you how, but you do it yourself. It's going to be a functor, but on the reverse direction. Okay. So if you have py here and so on, what you do is given a map. Yeah, I will tell you. You do this assignment, which is F inverse. Take a subset of y and send it to its inverse image. This is going to give you this assignment. So if this is contravariant, it is customary to write an op here. Okay. Now show that this is an equivalence of categories. Now, therefore, an order theorist can somehow talk to sets, some set theorist. All right, I should stop here, but give me a minute. So do you see that I have erased some example, but you had Finbeck op to Finbeck. So if you look at all these examples, this is a natural occurrence that you have op on one side, op on this side, op on this side, and there will be so many such examples where you have an equivalence of categories, but on one hand you have an opposite category of a well-known category. That is called the idea of a duality. So a duality is an equivalence of categories where on one hand you have an opposite category. So a duality is a functor or is an equivalence of categories, or if you wish, part of an equivalence, F from C op to D. So this notion of equivalence of categories where one side is op is somehow trying to tell you that there is some sort of a mirror dimension where if you have a property here, the dual property hold there, something like that. In the last talk, you have seen ideals and filters, something like that. So nonetheless, to emphasize more, I'd say that we don't really understand what a theory is, or if we even do that, there are two different manifestations of the same idea. In the latter lectures, you will see one side of this is going to be syntax category, another is syntactic. And so one side is syntax, you have another side semantic category. So they're going to be just two different ideas of representing the same theory. And that is going to be dualities. You will see lots of them in the coming future. I'll stop here. Yeah. Okay. So I think I have very little time. Come on, I have used 5 minutes. I gave you 5 minutes yesterday. Fine. So I will gloss over a lot of details, but the idea that I have to present is a pretty interesting idea, which I think, first of all, should I erase this if anyone has no problem? Okay. Idea which I want to talk about is that of very much lands in the is in the land of both philosophy and mathematics.
Give me a minute.
Yes.
Is there any question? I forgot to ask.
Okay. So, should I erase this? Yeah. So, and that is the idea of capturing things behaving in exact opposite manner. And to get it started, let me begin with a motivating example. So you have seen topological spaces and sets. So let's remind ourselves of this functor, sets to top, which takes a set S and maps which maps set S to its discrete topology. This is a topological space we all learned, and because this is such a trivial topology, any map of sets will be a continuous function. Every subset is open, so inverse of every subset will also be open. So that's one functor. In some sense, it's making a topological space out of a set in the least effort possible. By enforcing least effort, you're making a topological space. Similarly, you have top to sets. What does it do? Well, here's a topological space with some topology, tau x, and here's a continuous map, tau y. What you do is you forget that you ever had a tau x. You just map the same, and any continuous map in particular is a set function. So this is a valid map, valid functor. This is making a topological space from a set, and this is doing in some sense opposite of it, taking a topological set and giving you x. And these are things which happens a lot of times in mathematics, as we will soon see in examples. So let me write this as a functor free, giving you a free topological space, least effort. Similarly, this had almost no effort to make sets. From a topological space, you can make many sets by maybe looking at tau x and looking that as a set, you can make another set. But this one is the most obvious. So this is the underlying. Okay, here are two, but not only they are similar in that one goes in the other direction of the other. They are similar in this sense. So suppose you have a set S. For shorthand, I will denote this as U and this as say D for discrete topological space. That's just notation. So suppose I have a set S and I had a topological space X. So I'm looking at its underlying set. So U x tau x, which will be just be U, and this is in sets. Suppose this is a map F. Okay. What it is doing, it's taking an element and mapping it to element Fs in the set S. This is just a set map. With this, I can make the following map. I applied U here. Now I'll apply D on the other side, and I will get discrete space out of this, which will be S with its power set topology. And I used U here, but nothing here. I used D here, now nothing here. So X. Yeah, X as a set. So X is a topological space. This is in top. So if you take any element here, can you define me again? Can you give me a map here, which will be a continuous map with just the information of this F? It's fairly simple. You have a discrete topological space here. So any open set, its inverse, well, it will be a subset that will be open. So I can literally use the same thing here, Fs. This is continuous. But just for distinction in sets to top, I will just add a little tilde over there. So what this is telling you is that a map from S to U, S to UX gives me a map from DS to X. In the so it's once I'm applying U on the one side, now I'm applying the other functor on the other side. Okay. Now, what? So that's one side. You am getting a topological map from a set map. I want to get a set map from a topological map. So in order to do that, I need to clear some space. Let me do this here. So in the other side, what I will do, I will begin with a map from DS to X. All right. This will be in top. This is a continuous map. For the sake of distinction, we make it G. This is a discrete space on S, and this is again taking, this is S comma PS. And this is taking an element S to GS in top, but I can get a set map out of it again from S to underlying of UX, tau X, which will be simply X by taking S. Now this is I want a set function here, so well, I can just take G as it is. So S to GS. And this is in sets. And a very simple, and for again distinction, let me add a shriek here. So from G, I'm getting G shriek, and from F, I'm getting F tilde. From sets to top, from top to sets, and a simple verification will tell you that G shriek and its tilde, that will be a map in top again, using the same procedure, will give you back G. And this is a very nice result of our intuition that these two things were supposed to capture some sense of being opposite of each other in least effort possible. In fact, this tells you the following: that is all set maps, all functions of this form U X tau X in sets are in bijection with all ds to X tau X in top. And this bijection is of course sets. These are the sets. In particular, with the notation that we know, this is the following: Holmes in sets of S to UX, just to be very compact in notation. And this is same as home top from discrete space over S to X. And note that how we managed to get this bijection between sets. We didn't do anything artificial. We didn't do anything situation specific. We just noticed that the most obvious choices of mappings between them leads me to this bijection of sets. And now here's a condition which is very technical, but we won't cover it for the fact that we don't have much time, that this is in that precise sense that we don't have to do much effort is natural, that this isomorphism is natural. You shouldn't do anything very situation specific in order to get this bijection. It should, if you have a very natural reason to believe that this isomorphism exists, that isomorphism will give you a natural isomorphism. And naturality is, of course, in with the notion of natural transformations we develop, but maybe we will leave that for tutorial. So this motivates you. I mean, this motivates the following definition. So I will state here. So you can see how things are interchanged here. One functor here, nothing here, other functor here, nothing here. And this is precisely captured in the following definition. So you begin with two categories, take two cats, say C and D, with the following functors. With following functors. So you have this situation where you have one functor. So you have two categories, C and D. Yes, thank you. And C to D, one from C to D, a functor from a functor L from C to D, and the other functor in the other direction R. We call them, L is said to be the pair L comma R. The pair L comma R is said to be adjoint, if the following condition is satisfied. Adjoint. That is, you have your this is just this definition, this result that we observed, that you begin with C, take an object here in C, and so let me write this and then I will explain the other side of these L, C to D. So this is true. So L and R is said to be adjoint if for each object, for each C in C and D in D, the following happens. And just to make sure that you don't need to be very, you don't need to behave very badly in establishing this isomorphism should be natural. So this is a definition of adjoint functors. These Hom sets being the same. We will see that just by these we can get very nice properties about L and R in the tutorial. So that's the definition. And when L and R are adjoint, we say L is left adjoint to R and R is right adjoint to L. And we denote it by this symbol, one that you saw in the bottom of lattices. So you have that as the definition. And let's see some more examples. One of the, in fact, a very big class of examples of adjoint functors come from exactly these type of constructions. You take sets on one side and some other nice category which you care about, and you make you make those objects with least effort possible and just look on the other side their underlying sets. In particular, the following functors are also they also behave in the same way. You begin with the category of, say, abelian groups. Sets to abelian groups, and you make a what is called the free abelian group functor, and you forget the structure of an abelian group, you get back sets. So this is called the forgetful or the underlying. It's interchangeable. Forgetful. And this turns out to be an adjoint functor. Just like when we, in our motivating example, we removed this by top and we got the adjunction. That's one example. Similarly, you can remove app group by say by top, as we just did. You can remove it by pointed sets, as we did. We can remove it by vector spaces, which we did, and we will get the same behavior. You get sets to each of these as a free functor. You can take a free topological space that will be discrete space, sets with pointed, sets with the objects of this category are sets with a attached symbol onto it, a distinct symbol onto it. So that's one of, and the underlying functor here is that you forget that functor. Yes.
I don't understand the idea of forgetful functors.
Sorry.
We have used the forgetful function.
Yes. Yeah. Okay. Let me explain. So maybe this will be a bit too technical to explain. This is simpler. Do you understand the case in top? When we took the following, you have top on the right side, you have sets on the left side. You make the free topological space out of a set by giving it the discrete topology.
Yeah.
And you get a functor from top to sets by forgetting you ever had a topology. So you have x comma tau x here, and you map it to just x. Yeah, that's what I said, right? Forgetful, underline, they are same things, just a different name. Yeah, is that clear? Yeah. So you can similarly have that for, you can replace this by vector spaces. You will get the same thing. You will have a vector space plus 0 action by R, and you forget that you ever had those structure of abelian group and action by R. So you get these things, and this will be the free vector space, and this will be the underlying set. Okay, so in the rest of the time, let me give you some examples of adjoint functors, which is something very much in the line of what we've been looking at for the past day. The first example is from topology. So you begin with a topological space X, this tau X in top. You look at all of its subsets of X. You look at all of its subsets under inclusion. This is a poset. You look at all the closed subsets of X. So maybe I will write this as Cx under inclusion. You can define a functor when you treat them as categories. Every poset is a category. Order preserving maps will then be a functor, as we saw. So here's one functor which takes any set S, subset S of X, and maps it to its closure. Right? That will be in closed sets. And here's another functor that takes a closed set and includes it into Px. Every closed set is again a set, a subset of X. So it takes a set and just includes it into this. Now note the following. If you have a closed set S, so a set S, you take its closure, it is contained in a closed set if and only if S is contained inside of C, right? It's closure, so it's the intersection of all the closed sets which contains S, and you can deduce that very easily from there. There's nothing to deduce actually. So, and also remember that a poset is a very special category. Between any two objects in a poset, there can at most be one arrow as a when you treat those posets as a category. So what does this tell you? This tells you exactly this, that Hom in Px is of Cx from S bar to C is naturally isomorphic to Hom of Px from S to C. Right. So S is a, let me just write this as I for inclusion and denote this as this, or if you want to be very explicit, this. So this closure and inclusion. So this will turn out to be closure of S to C, and this will turn out to be inclusion of C. And this is exactly this, right? So this is a pair of adjoint functors. So that's a topology, example of adjoint functors in topology. Okay. Right. So another example, most of the approachable examples of adjoint functors are do come from posets. And in fact, this example is so much common that it has a very nice generalization to arbitrary posets, which has a very famous name. Should I remove this? Okay. In fact, a different version of it, of what I'm about to explain, is the topic of Galois theory. So here's a definition. You have two preorders, or if you like, take them as posets even if you wish. Suppose P and Q are preorders or posets, whatever you like. And you have two order preserving maps from P to Q and G from Q to P. These are order preserving maps, or order preserving maps. Then we say that F and G establish then F and G establish a monotone Galois connection if the following happens: that you begin with any element of P, you apply F, you get this in Q. In Q, this happens if and only if P is less than equal to GQ. So what this tells, this is in P. Or in other words, what this tells you that if Hom in P, Hom in Q of FP is FP to Q is same as naturally in P from small p to GQ. And this is for all P in P and Q in Q. So this is the monotone Galois connection. This word Galois you may have heard refers to work of Galois, but what the main theorem there is of opposite of this, that is called antitone, but I don't think I have time for that. Okay. So just as a last remark, this is, first of all, it should be natural, and most of the time it will be natural if you are careful enough. And this is also a monotone Galois connection, because posets, order preserving isomorphism, which is natural. Any questions from online audience? Because I don't have time, then I think the other examples will be in the tutorial, which we will discuss. Any questions?
So monotone Galois connection is specific only to posets, is it?
You can, at most, you can be, in the full generality, it will be for pre-orders, because I don't use any anti-symmetry here.
Okay.
So this will hold for PQ being pre or partial, for both. If it's holding for pre, then of course it holds for partial orders.
What is the corresponding theorem you wanted to state?
Corresponding theorem for what?
You said that you are going to state a theorem. This is just a definition, right?
Yeah, this is a definition which generalizes this. And there's another example of monotone Galois connection coming from group theory. The antitone Galois connection is where the fundamental theorem of Galois theory is. Sorry?
We'll say it tomorrow.
Yeah, I will say that tomorrow. Okay. So
you say that this is a definition, we wanted to be a theorem, right?
What?
I was expecting to say that you state the theorem.
Theorem in what? Adjoint functors or in Galois connections? Well, these are all examples. Oh, okay. So this is a monotone Galois connection. Monotone Galois connection. This is a monotone Galois connection. This is also an adjoint functor, an example of an adjoint functor, and the whole class of monotone Galois connections are forms a good example of adjoint functors. So this is itself this whole class of yeah, this forms a what we call the adjoint. We define the adjoint functors. Adjoint functors, when in the case of pre-orders, correspond to monotone Galois connections when we have order preserving loops. The other theorem will be in the tutorial, maybe.
Okay, so we end our session now, and we come back after lunch at 2:30 for next session. Okay. Now, thanks for the speaking.